Hello everyone, I am Hu Lin from the MSTP LMT department. I'll introduce the EoS Service Protection in this course. Protection modes commonly used for Ethernet over SDH EoS services include LCAS, LAG, DLAG, ERPS, STP, RSTP, MSTP, and RPR. This document describes these protection modes one by one. LCAS is a protection technology applicable to virtual concatenation channels. It can dynamically add or delete VC trunk members to adjust bandwidth without interrupting services. It can also shield failed members in a VC trunk and allocate services on other member channels to avoid service interruptions. The animation in this slide shows how a VC trunk member is added or deleted and how a failed VC trunk member is deleted and recovered. LAG is used to protect Ethernet links. It combines multiple Ethernet ports to form a link aggregation group to increase bandwidth and improve link reliability. LAG is used between neighboring devices and is simple to use. LAG has two types: manual link aggregation and static link aggregation. A manual LAG does not use LACP and needs to be configured when a device is interconnected to another device that does not support LACP. For a manual LAG, when a unidirectional fault occurs on a member link, the transmit end cannot detect the fault. As a result, the services are interrupted in one direction. You need to use other detection methods, such as configuring ETH/OAM on ports to monitor the link status. A static LAG uses LACP and does not have defects as a manual LAG does. When a device is configured with a static LAG and is interconnected to another device at the peer end, the peer device must support LACP. LAG load sharing has two types: load sharing and non-load sharing. Member links in a load sharing LAG share service traffic. The load-sharing hash algorithm supports calculation based on the source and destination MAC addresses, source and destination IP addresses, and MPLS labels. When a member link is faulty, the system recalculates the load-sharing mode. In a non-load-sharing LAG, only one member link is in the active state and carries service traffic, and the other member links are in the standby state. When the active member link fails, a standby member link will be selected to carry service traffic. LAG non-load sharing has two modes: revertive and non-revertive. In revertive mode, services are automatically switched to the working channel when this channel recovers. In non-revertive mode, services are not switched to the working channel. DLAG is an interboard link aggregation group and provides board-level protection for ports. It can detect unidirectional trails to implement 1+1 protection for interboard ports. A port on the active board and a port on the standby board form a DLAG. The port on the active board carries service traffic, and the port on the standby board is in the standby state. When a board, link, or port is faulty, services are switched to the standby board. You can set the system priority and port priority to determine the working status of the DLAG. The device with a higher system priority is dominant in the DLAG, such as LACP negotiation and port mode setting. The port working mode is determined according to the port priority. A port with a higher priority is the working port. DLAG supports revertive and non-revertive modes. ERPS achieves quick Ethernet protection switching by using the Ring Automatic Protection Switching (RAPS) protocol. ERPS uses an independent VLAN channel to carry RAPS messages. A control VLAN ID cannot be the same as a service VLAN ID. The RPL owner blocks its East RPL port to avoid a loop. When a link or an NE on the Ethernet ring becomes faulty, the RPL owner unblocks its East RPL port so that services can be transmitted through the East RPL port. After the link or NE recovers, the RPL owner blocks its East RPL port again. Services are switched to the original trail. STP, RSTP, and MSTP are all used for the Ethernet ring network. These protocols block redundant links by using an algorithm and prune the network into a tree topology. This avoids loops, broadcast storms, and MAC address entry flapping. STP, RSTP, and MSTP transmit Bridge Protocol Data Units, BPDUs, between bridges to specify the root bridge, root port, and designated port, and block other ports to avoid loops. Both STP and RSTP generate only one spanning tree. RSTP achieves faster network convergence than STP. MSTP is compatible with STP and RSTP and is used to generate multiple spanning trees based on VLANs. STP sets up a spanning tree as follows. 1. Selects the root bridge. The bridge with the smallest bridge ID is the root bridge. Each spanning tree has only one root bridge. As shown in this slide, bridge A has the smallest ID and is the root bridge. 2. Selects the root port. The root port refers to a port on a non-root bridge that transmits frames to or receives frames from the root bridge. Each non-root bridge has only one root port. As shown in this slide, the root path cost from BP1 of bridge B to the root bridge is 5, and the root path cost from BP2 of bridge B to the root bridge is 14. Therefore, BP1 is the root port of bridge B. The root path cost from CP2 of bridge C to the root bridge is 9, and the root path cost from CP1 of bridge C to the root bridge is 10. Therefore, CP2 is the root port of bridge C. 3. Selects the designated port. Select a port on the link between bridges as the designated port. As shown in this slide, port BP2 of bridge B is the designated port, and port CP1 of bridge C is the designated port. 4. Blocks the CP1 port. STP port status includes blocking, listening, learning, forwarding, and disabled. RSTP reduces 3 port states and defines 2 new port roles to ensure rapid switching port status. RSTP adds the alternate port and backup port, combines blocking, listening, and disabled states into the discarding state, and supports rapid switching of port status by defining edge ports and the point-to-point attribute of ports. As an enhancement of RSTP, MSTP can generate multiple spanning trees based on VLANs. RPR is used to transmit IP data on an SDH ring network. It allows data to be transmitted bidirectionally along a ring between the transmit and receive ends. This improves bandwidth utilization and provides protection switching of less than 50 milliseconds. When a network fault occurs, wrapping protection switching is triggered first. When new service trails are created, steering protection switching is triggered. That's all for this course. Thank you.